we have negative time. I was trying to help out.
It's the other help. The staff time.
So, when last we met, I got myself sort of messed up staring at what turned out to be, and this is all I'm going to say, was a trivial vector identity, which had to do with A cross B dot C equals B dot A cross C, or something like that. They have to be identical, as long as you keep things in order. I found myself standing here staring at it, wondering how I got from here to there. And then I just sat down and began to write out the actual product and realized that it was so obvious it wasn't even an identity in Shams, right? So there was that.
Triviality beyond triviality.
So I'm just leaving it at that. I just, somehow I lost my brain. But then there was something that was more subtle that I have not thought about. And that had to do with full derivatives and partial derivatives of B with respect to time. I'm just going to assert that I must have done it right, and I posted the notes the way that they were. And if you have a problem with them, then tough.
Go eat a shoe.
No, actually, if you have a problem, if you find something wrong, please let me know. But don't announce it loudly in class. Just, very politely let me know at a later time. Okay. Unless it's a factor of C or a factor of 4 pi or a minus sign on the board here. Okay. If you know that, then definitely let me know.
Professor.
Yes.
This isn't ours.
This isn't ours. Joe, Monty.
It isn't ours? When did you become more than one person, Joe?
He was speaking for George.
No, Tim and Ian.
Oh, okay. He was speaking for Tim, Ian, and himself.
We agree with his pronunciation. I mean, I actually have noticed that some professors actually do just speak in the second person, or no, in the first person plural.
Does?
No, if in first person plural, they just
Yes.
I've noticed a bunch speak in
That's a royal way, because we are royal. We have been tenured. We are royal. We are.
That's an awfully strong statement.
What do I want to say?
And it's impossible to get rid of them unless they show naked and drunk. I know.
So last class we talked about things that change with time. Magnetic field changing with time, giving rise to a curl in the electric field, and electric field changing with time, giving rise to what we call the displacement current, which is the curl in the magnetic field. So we had, I'm just going to remind us. And I might have lost a 4 pi in there, but we'll just leave it like that. There are consequences of that, practical consequences. And so what I'm going to talk about at the beginning of this class is the idea of inductance and the fact that that is a consequence of the equations that I just wrote up there. But I'm going to, let's say initially, just talk in terms of a quantity that I'll call the mutual inductance of a circuit, and then we'll come back and find out what it actually turns out to be. So if I have a circuit over here, and a circuit over here, right? I drive current through that circuit, so maybe I've got to finish it over here, and I'll just twist some wires out there and put a battery in here. To drive current through that circuit. Or maybe I'll put the battery in the circuit. There we go. Battery in the circuit to drive current through that. That gives rise to magnetic field. And remember, by the way, if you get far enough away, the magnetic field looks like a dipole. So the lowest order might look like a dipole. So I'll just sort of draw a magnetic field from that. I've got to complete the lines, but I'm not going to complete them here. This magnetic field passes through that circuit, and there's some net flux that flows through that surface. We'll call the net flux that passes through this circuit over here to be the magnetic flux linkage between the two circuits, right? And actually I should define linkage now. I'm going to do it in a very simple way. First of all, it's the flux. But if I had a circuit that looked like this, that was multiple turns, each turn of the coil that I go through is going to give rise to some net flux through the entire circuit, right? So one turn is one flux, two turns is two flux. So I might put the number of turns times the flux through one coil. And that's what I'm going to be calling the flux linkage. Okay? So the flux linkage through some circuit, let me call it the nth circuit in some array of circuits, right, is going to be equal to all the other sources of magnetic fields. I'm going to define it this way. Sum over all the other circuits, some term that somehow links the current in circuit K, so this would be circuit K here, to the current, to the flux, or circuit K, to the flux that passes through circuit N. And I've just written that sort of as a general thing to have any number of circuits, right? But I actually know from the first equation there that the EMF that's going to be generated in circuit N, right, is the time derivative of the flux. And so I'm going to have C sum over all K of the other circuits, M, N, K, T, I, A, T. And this thing here, well, actually, the reason that I wrote this is a definition, right? It's the definition of this term that couples the current in one circuit to the flux that passes through the other circuit. That term there is called the mutual inductance of those two circuits. But then Maxwell's equation tells us that if I have mutual inductance, then changing the current through one circuit gives rise to an EMF in the other circuit, right? That's the basis for the transformer. And that's as much as I'm going to talk about transformers in this class. But varying the current through one circuit yields an EMF in the other circuit. If this circuit had a resistance to it, then current in this circuit would give me current in that circuit. And the ratio of the two currents would depend upon the resistance, and it would also depend upon the mutual inductance of those two circuits. Yeah, okay. I want to now look at what's actually going on on the what do you think about this? In this equation here, and attempt to deduce in some general form what the M here must actually look like. All right, so that term, that flux over there, is into the integral over the a surface bounded by that circuit with the appropriate topology, right? So the circuit is a complete circuit that's got to go, it's going to maybe crossing over itself, and for each element of the surface we have to make sure we've got the sign right. So we have to be a little bit careful about actually doing that. It's not just the projection of the area, it's depends upon what direction we choose a direction around the circuit, we've got to be careful about it. Let me just put it that way. So over the nth surface area, being careful about it, the magnetic field from the kth circuit, all right, got it into the surface normal for the nth circuit, right, is going to be the actual flux, right? So that has got to be equal to this, which is equal to that, right? And where we're going here is that we want to find out what that mutual inductance between the nth and the kth circuit is going to be. That's the vector potential from the nth circuit. And now using Stokes' theorem, around the nth circuit, this is the vector potential from the kth circuit. This is the source. The nth circuit is the one that's picking that up. Right? But the vector potential for a particular current is actually known. You can go ahead and substitute that in. And yeah, this is an EMF over here. And because this is an EMF over here, this is the integral around the nth circuit, right, of E dot D Ln, from which we deduce that the mutual inductance between the nth and the kth circuit is 1 over c squared. By the way, once I finished giving you the plausibility argument for where this comes from, we're never going to use it again.
We're never going to use the mutual inductance or the argument?
The argument.
Ah.
Oops. So these are positions in each of the two circuits, and what we're going to do is go around the circuit, form a closed path along the wires, for example, in the circuit. DLK dot DLN. So this thing, the mutual inductance that links these two circuits, you might have guessed this already, you know them already, does not depend upon the currents in the circuits or the magnetic fields or any of those things. It's a geometric quantity that's calculated by doing two line integrals. Doesn't matter what order we do the two line integrals in. And therefore, by the way, it doesn't matter whether this is nk or kn. That is, we can equally well, just looking at that, we can say that phi sub k is equal to, actually, let me just do a pair. There. Now I've done a pair. Right? Phi sub k is equal to C M K N I sub N. Right? So I drive current, a current through the circuit. I get a flux through the other circuit, or I drive a current through the first circuit, and I get a flux through the second circuit. These two numbers, these two mutual inductances are the same. And so it turns out that it actually doesn't matter which of the two circuits I drive. I take a current. I'm going to drive a current through one circuit or through the other circuit. I drive current 1, or current A, through the first circuit. It gives rise to a flux through the second circuit. I drive the same current through the second circuit, through circuit B. Current B through A. No, current A through circuit B, through circuit 2. I'll get the same flux through circuit 1. That is, that they are mutual. Drive a current, get a flux. Drive the same current, get the same flux. Even though the two circuits can be weirdly different shapes, that mutual inductance is completely mutual and relates the current in one to the other, and the current in the other to the first one. Back again. That can make, so that's the important point that comes out of writing all of this out and just realizing that the expression for mutual inductance looks like that. Right? It doesn't matter what order you do your integrals in. It's completely symmetric. This formula here is known as the Neumann formula. And I have a note here to myself, I already said this. It's not really useful for calculations. But it gives you this, these 2 points. One is that M21 is purely geometrical. And the second is that the integral doesn't change if we switch the order. So it's mutual between the two circuits. So let me give you an example of something that's hard one way and easy the other way.
You have a question.
Yeah.
So is that a tensor or?
I don't know how it transforms under Lorentz transformation. So I'm going to say no. It's a n by k matrix. Okay, not necessarily. Yeah, I don't think there's any way that's going to transform appropriately. Yeah.
So n can be a large number of circuits.
It could be.
So you.
Well, no. Okay. On the left-hand side, I'm choosing the nth circuit in the device. On the right-hand side, I could have a whole bunch of circuits giving rise to a flux through that one. But what I did, I erased the sum and said, let's just consider a pair. And with any whole bunch of circuits, you can always consider them in pairwise as pairs. And then in the end, sum up all the mutual inductances to find out the relationship between the currents in that guy and the flux through that one, or those guys and the flux through that one. But right now I'm just talking about pairs.
Right. So, but even with the sum, you're still only calculating the flux through a single.
You are in the act, yeah. Yes.
So doesn't that mean that n can only be 1 in any
N is 1.
calculation?
Yes.
So
I'm sorry.
So wouldn't mk be a vector instead of a matrix?
Well,
Oh.
no.
Yeah, I'm just saying it's not a tensor.
Okay.
No, n is no. You got n. N can be any particular number, but n mk.
Yeah, let's say I could have, and here's where it might be a matrix. I could have a total of capital N circuits. Right? And that will give rise to n times n mutual interactions. And I could create a matrix of those n times n mutual interactions. And then ask, what's the output on this particular n? Little n. But it's not a tensor. I'm just deciding what definitions to leave up. I'll leave this one. And that's about it.
Not the Neumann formula?
Don't need this. I'm not going to use it ever again.
I thought you would have liked the lip in your hand.
Not even on a test.
Can there be a multiple choice problem where we have to pick that one out?
Yeah. All right. So here's the problem. And by the way, this problem is a problem from experimental physics. I have a solenoid, a long solenoid, not infinite, but long enough. All right. Then I put another solenoid inside of it.
No, but you have to
What?
you actually have to do it in XFIS.
Most of you have had XFIS, right?
Yeah.
Okay, this is the, and then by the way, then I put a piece of metal inside the solenoid, so it's like Russian dolls of electromagnetic theory. But the thing that I want to, we want to think about now is, if I drove current, some current I, through the inner solenoid, what would be the flux through the larger solenoid? And the reason that I want that is because while I'm changing the current in the inner solenoid, it's going to give rise to an EMF in the larger one. But the problem is, and actually I should use the flux linkage through the larger one. Because the field that's being generated here in the small one is doing this. It's passing out through the sides of the big solenoid. So I could ask the question, you know, if we're given current here, what is the flux linkage through the big one? That's a really hard problem to solve, because you've got to figure out where all the lines cross through and how many turns are going to include a certain flux, right? Bad problem, okay? But because the mutual inductance is mutual, what I could do is switch the problem around and instead solve this one. Put the current through the big one and then calculate the flux linkage through the small one. That's an easy problem. So I can calculate the mutual inductance really easily. Once I've got it, then I can turn the problem around and say, I drive current through this one, and that gives rise to a flux through the other one, so I know what the EMF of the second coil is going to be. Okay? It's cute. All right. So let's go ahead and do this one. The magnetic field due to the big coil, let me call this coil 2. That's coil 2.
Yeah, you actually have to put an experiment.
This one in here, just so you can see it better.
Isn't there a piece of metal inside the inner one, right?
In XFIS,
What is this one?
there would be a piece of metal in there. In this problem, there's no piece of metal in there. But what you could think about is, what if I didn't have that inner coil in there, and I just had a piece of metal in there, right? And now I want to somehow calculate the mutual inductance of those two things, right? It's actually really easy to calculate the mutual inductance if I just put a short piece of pipe. It's quite a bit, a tubular pipe. It's quite a bit harder if I've got a solid piece in there, but not that awful. It's something that could be done, right? So to solve the XFIS problem quantitatively, you'd actually have to put that chunk of metal in there and then integrate across the cross-sectional area of the chunk of metal. You'd find the mutual inductance for every element of the chunk of metal. But with this approach, it's doable. If you worked it the other way around, it would be a really hard problem. All right, so the magnetic field due to current I flowing through coil 2, the big one, is going to be uniform. And we solve this problem. It's 4 pi over c n2I, where n2 is the number of turns per unit length in the large coil, in the long coil, right? So that means then that the flux through the short coil, the flux linkage through the short coil, is N1, A1, B2. Wait a minute, let me think about that for a second. That is the total number of turns in the short coil. So let me put the length of the short coil in there. I left it out in my notes, but there's got to be a total number. It's just NAB, if you remember from physics 2.
Where A is.
So that's N1, L1, pi, R1 squared, because that's the cross-sectional area, 4 pi over C, N2, pi 2. I'm driving current through coil 2. So, but is it, I'm just talking generalized current here, it's the same, being input into both coils, which means then that the mutual inductance between the two coils is 4 N1 N2 pi squared A squared, oh, sorry, R1 squared over C over, wait, times L1
Where did you get the pi squared? Wait,
I got pi squared, I got 4.
That's it.
4 pi over c times that pi.
Yeah, I see it. So.
Yeah.
Mu naught. That was
Here's
right.
my problem. I want it L1 and L2 to be mutual. They're not. Never mind. It's the short coil that controls the mutual inductance. Never mind. It's good. All is good. That's it. All right. Once I know the mutual inductance, then I can drive current through the short coil and know what the EMF in the large coil is going to be. I think that's sort of cool. All right. So that's mutual inductance, and we just made a transformer. That was between two circuits, but actually we know that if we have just one circuit, that the changing magnetic flux passing through that one circuit is going to generate an EMF in itself. So we drive current through a circuit, through a coil. It's going to generate, when that current changes, or rather, that current passing through a coil generates a magnetic field. If we try to change the current in that coil, it's going to generate a changing magnetic field, which will generate a changing flux through its own coil, through itself. That changing flux is going to give rise to an electromotive force, which is going to be generated in a direction so as to create a current which opposes the change that you're trying to make in the circuit. So I'm going to define one more inductance, which is called the self-inductance. That is the flux through a circuit is equal to, the flux linkage through a circuit is equal to the inductance of that circuit times the current is passing through the circuit. We don't need any N's or K's or anything like that, because it is the circuit itself that we're talking about. Did I drop a C here? Probably.
To have it have the same units. Yeah.
I wanted to have the same units, and I have a C there. So I'm going to keep a C here. Okay. But it's quite likely, because I lifted some of my examples